Well, hey there, AP Physics. Time for a little homework help. I honestly thought I had this one already on YouTube, but I went through to go double link it into the classroom, and nope, guess not. So I decided to take a little time after school here and make sure you had a little help where it was necessary. Okay, so let's begin. This is the number 7. There are 2 questions, I believe, on number 7. And you know what? Actually, I'm going to start with the second question. So, the cannonball question. Let's begin there. This question, first of all, I just don't think should be that difficult for you, right? We are looking for that initial kinetic. Okay, maybe that's not what I need. Let's try that. Sorry, guys. Let's try that. So the kinet. Okay, what the heck, man? This is killing me. The kinetic and. All right, I'm going to have to restart this video if this doesn't knock off. The kinetic and there we go. The kinetic energy at the beginning of the launch becomes potential energy at its maximum height. Do realize that when you're launching something at an angle like this, that you are dealing with, obviously it's only the y component of the velocity that is going to turn into potential energy. However, you will still have kinetic energy at the peak of flight based off of the horizontal component of that. So make sure you take that into account when you are working on the one that is being shot at an angle. The one that is being shot at 90 degrees obviously is pretty straightforward. It's rather like this. But the one being shot at 37 degrees is going to have kinetic energy initial. I mean, I suppose you could consider all of the velocity of your 800 or whatever your number is, meters per second, is going to be your initial kinetic energy. But at the peak of flight, you will have potential based on the height attained by the ball, plus the kinetic energy from the horizontal component, because it's moving in that parabolic arch. Now, keep in mind, you're going to need to figure out how high the cannonball actually goes, and that is based off of the sine component of that speed. Okay, and the cosine component is going to help you find that. So be careful for those, but not too tricky. It's just bringing in the whole projectile thing. This one is definitely a more challenging problem, at least in terms of the algebra and even the conceptual understanding. So let's begin. Assuming this is my first snapshot, right? And so what happens? The first one drops down to the bottom, right? And the second one is up here. And then my third snapshot, the first one is down at the bottom, and the first one actually flies off the string and goes up. All right, so it's on its way up here, but then the string loses tension and the other one goes flying. It's like an experiment gone wrong. So we actually have a few snapshots here. Let's keep that in mind. So here, of course, we just have the potential energy for M1. Right? When this happens, this intermediate step before it goes flying off into outer space, right? At this point, you have kinetic energy from this block, plus here you have kinetic energy and potential energy again for the second block. That's where you're going to be solving for this guy right here. All right, you are going to get, and take a look what they want you to put it in terms of M1, M2, and G. So you have 2 different kinetic energies in this system when you're figuring out your velocity of M1 hitting the ground. It's not just potential to kinetic. You have to consider everything in the system, which includes both of the blocks. Now, for the second piece of this, find the maximum height to which M2 rises. Okay, so what's happening in this third step is what was originally kinetic energy, say it was down here, becomes a new potential energy here. Now, you do know already some of this height. It's the height that the block went up in the first place. So I don't know if you want to call that 1. That works, right? But this new height is independent of that. It's a new height, And really, H1 plus H2 is what you're looking for. That's your answer that you're trying to find. Now, what I would suggest is focusing primarily on these two. And the rest of it doesn't really matter because all that other stuff was just to get the block up to its whatever height. But it's only the kinetic energy when the string loses tension that's going to give it the new extra height when it leaves the pulley system. Okay, so keep that in mind as you go. This is going to be dependent upon that kinetic energy becoming potential energy. And you're going to obviously solve for H. But, of course, it's going to get tricky because when you do that, it's actually a pretty easy calculation. But when you get your answer, it has V in it. And if you look again at this, you cannot use V, which means you're going to have to take this answer and substitute it into your answer over here that you were finding. Okay, I realize that's a little nebulous without actually doing all of the math for you. But keep in mind, you're going to find H, you're going to solve this relationship for the extra height that it goes up from kinetic to potential. When you do that, you'll actually get a pretty simple answer, but it will have the variable V in there. You cannot have that. So take your velocity from your first answer and substitute it in and simplify it, and you'll end up with a big, messy fraction square root thing. So awesome. Have fun. All right, but that's what you're doing. If you cannot get the thing to work, like it won't accept your answer properly, but you're pretty confident in your answer, come see me. I can check it and I can manually adjust if needed. But also remember, according to someone who is struggling, subscripts matter. So make sure you put in things with like M1 and the 1 is subscripted. It makes a difference. Okay, on that happy note, we did that. Let's move to the next. Okay. So this one has got some terrifying little graphics in here. Makes you think the problem is really difficult. But actually, it's not so bad, right? So the block is pulled 4.4 centimeters. So let's assume that this is the top part right here. So 4.4 centimeters. Make sure we change it over to meters, people. To the right of the equilibrium and released from rest. Since it's from rest, that tells us all we have is spring potential energy. Find the speed of the block as it passes through equilibrium. Okay, at equilibrium, we know that all that spring potential energy has changed to kinetic. Okay, so that's part A. Part B says, not so fast, people, because we have some friction. So same idea, same initial US, but now for this third guy here, I don't even know if this matters, like if it's really the third one, but let's assume. So our second situation here is, okay, so all this spring energy that's out over here is still the same spring energy we're going to start with, but now we have some friction. So we have to either put that there or we can say this, minus the work done by the friction gives us the kinetic energy. Either one will give you the right answer. All right, so you're given a coefficient of friction so that will help you figure out your force of friction that you can then use right here to do your work. Okay? I don't even know why they have a graph in there. I think they're just getting silly. Unless I missed something. It's very possible. All right, last few. These are tricky. Atwood machine, energy style. So you're given a distance that this block is going to fall. So let's consider that the bottom of whatever number you get, I got 1.90 meters, that this is my zero mark. So from here to here, my 1.90 meters, that makes this the zero. Now, let's also keep in mind that this block here is not moving at first. So the entire system is just potential energy from this block. However, as this one drops down, right, let's say this is block number 1, and let's say this is block number 2, just to make it easier. So the initial potential energy gets changed to what? Well, kinetic energy of block number 1, because it will be moving when it gets down to the ground, plus kinetic energy of block number 2, because it will be moving this away, right? But also notice they have the work, or they have friction here. They give us a coefficient of friction. So we know that not all of this energy is going to become kinetic energy, not all the potential energy. So you can either, again, you can put the work over here as a plus, or you could say, well, I'm taking it away from the potential energy. The good news is that both of these should be moving at the same speed. Why? Because they have the same acceleration. All right, they're going to move together. They're going to accelerate together for the same length of time. They're going to have the same speed. So you can take either iteration of this particular formula and work with it. Okay, number 4, softball pitcher. So this is talking about the pitch, right? Really what they care about here is you're given a velocity at the top, and you're being asked to find this velocity at the bottom. All right, let's consider what's happening here. Up here at the top, what kind of energy? There's kinetic and there's potential from the ball being off the ground. At the bottom, that's what we're going to make our 0. We have kinetic energy. However, also keep in mind that she is applying a force, and notice they're very specific here, in the direction of motion. So it's not really going in a circle the same way. We're not dealing with that whole work is 0 thing. We actually have work this time. All right, so the speed of the ball on the bottom is a combination of the original speed of the ball, the height of the ball, and the extra energy that she applies with her hand by doing work. Okay? So take all that into consideration. And remember, it is a circle, so when you figure out your height, you can use properties of a circle to help you with that. Last question, now that your brain is melty. So here we go with the skydiver question. 2 parts to this question. So the first one is pretty straightforward, right? So, okay, we have a drag force. That's what this is talking about here, a retarding force. That just means it slows it down, right? You've got your distance, your total. All right, so here's your skydiver. And he's falling, in my case here, 1360 meters. And so for a while, the parachute is closed. Let's say it's closed to there. It says 50 meters. And then it's open for the rest. So we have a drag force here that is pretty small. And then from here to here, we have a second drag force that's much larger. And we're being asked to figure out the velocity on the ground. So, okay, definitely kinetic energy here. Definitely potential energy here. But let's consider what's happening. We're going to take away the work from the first drag force. We're going to take away the work from the second drag force. And that will tell us how fast we're going at the bottom. The hope is that we will not be going too fast. Then part C comes along, and that one seems even crazier. Same premise, but you're not given any values or you're trying to figure out when to open the parachute. So you don't know any of the values where the parachute is closed. But you can actually solve it the same sort of way as long as you put in some variables. Right? So let's reconsider the same problem. Let's say, again, what did we have for our total amount? 1360. So the whole thing is 1360. And at some point along the way, this is when the parachute opens. And it's going to fall a certain amount. Let's call it X. Let's call it X1. All right, it's going to fall there. From wherever it is opening the parachute to X1. Well, how far is the parachute not going to be open? It's going to be the amount total minus X1. I don't know, let's call that X2. So you know your variables. right? In this second problem, we know the speed we want, so we'll be able to determine our kinetic energy. All right, we still know the total height. These two values for W1 and W2, we're going to use this for our distances that they are that the drag forces are being applied. And that will this xi will be or x1 will be the only variable that you're missing. Okay, so same setup, but now you're going to put in some different values for your distances. Okay, I hope that helps somewhat. I'm getting kind of tired, so I'm going to sign off and head home. Come see me if you still need help.